Okay, so today we're going to talk about pressure and how, well, pressure in relation to fluid statics. This statics part here is pretty important. And so what engineering questions are we trying to answer right now? And the question we're really trying to get at is, what is the relationship between pressure and depth in a fluid? So between depth and pressure in a fluid. Given that the fluid is at rest. This part is very important. This is what gets us the fluid statics pressure as opposed to other kinds of pressure. When fluids start moving, we're still going to be concerned about pressure, but we'll require very different models in order to deal with that. If you remember back to the first lecture in this series, I talked about what made fluid mechanics difficult, and that was how you learn one model and then you'll use it later, but it's not related to the other models, so they don't build on each other in the same way that it happens for some other classes. Well, we're getting our first lesson in that. Like I said, pressure for a fluid that is at rest, our model for it is very different than if it's moving. So, well, the answer to this is a very simple equation. The answer is pressure is equal to the density of the fluid times gravity times the change in height in the fluid that you're looking at. Great. So this formula and what I call rule number one of fluid statics are the two rules or two things that you need to absolutely understand about fluid statics. And this rule number one is that pressure in a fluid at rest, remember, in a fluid at rest, is the same in all directions. Oops, let me spell that right, or at least make it readable. It's the same in all directions at a point. So what this is basically saying, and we'll talk about this more later, we'll use it a lot too, is let's say we have a point in a fluid. No matter which way you look in that fluid, like left, right, up, down, I don't know what directions that is, into the page, out of the page. No matter which direction you look at that point, no matter which direction you measure the pressure at, so let's say we have a little pressure transducer that has a flat face on it, and we point that in all these directions. The pressure at all these points will be some pressure P, and it will be the same. So with these two rules, we can do a lot. With rule number one and with pressure is equal to rho GH, we can do a lot for solving engineering problems. So at a fluid at rest, the pressure is the same in all directions. Let's talk about why this is true. Let's kind of it's such an important rule, even though it's simple, that we need to do a derivation, if you will. So if we're trying to show that in a fluid at rest the pressure is the same in all directions, the question I want you to think about the question is always, what tool or model can we use to relate pressures and weight? Right? Because obviously the pressure is caused by the weight of the fluid above it. So we want to relate pressures and weight, and this is a mechanical engineering course, so our general answer is for a model to start with is usually sum of the forces is equal to mass times acceleration. This is like the basic model of all mechanical engineering, right? Most of it anyway. Mass times acceleration. So we can simplify this model, right? What do we know about our fluid? This is where I'm asking a question. not just talking to myself. This is where I ask a question, pause it, pause the video, try to answer it. But what do we know about this fluid that helps us simplify this equation? Try to make a guess at it. This is that active learning, remember? That engaged learning. You're trying to do stuff before I do it and not just copy down exactly what I say. All right, so what we know is that the fluid is at rest. So if the fluid is not moving, it cannot be accelerating. So this is 0. Fluid is at rest. And we're going to develop in a little bit a more systematic way of showing assumptions and how they relate to our models and simplifying them. So our fluid is at rest. If we, over here on this coordinate system here, let's draw a fluid element that we're going to analyze using our some of our forces equal to mass times acceleration. So this is basically the start of a free body diagram, right? So if we start drawing this, we're going to draw a wedge of fluid. Let's see how well I can draw this wedge. Here we go. This isn't the worst. It's not the best, but it's not the worst. Great. Okay, so here's our wedge, and this wedge has an angle theta here, and now we got to worry about the an angle theta. It has dimensions in this direction. This is a delta x, and remember, delta basically means a very small distance, almost a differential distance, right? This distance here is delta z, and this distance here is a delta y. Great. So now we got to start drawing our forces on this fluid element, right? So we know that there's gravity. So if there's gravity, there's going to be some kind of weight on it. I'm going to draw this acting on the middle of this element. And okay, so what is the weight of this fluid element? It's the taking my time here so you can write it down before I do. Hopefully you'll get frustrated and just be like, fine, I'm just going to write it down. Mass times gravity, right? On the left-hand side here, we have some pressure, Py, which basically means a pressure acting in the y direction. We have a pressure acting on the bottom, too, which is a P Z. We have a pressure acting in the x direction on this face, and a pressure acting on our sloped face, which we'll call PS for slope. And it's important to note that this length of this side here, we're going to call it a differential S, the length differential S. But we know that that length is related to the other lengths through this theta here. Great, and now there are other pressures too, right? This px is balanced by a px on the other side, but we're just going to draw these for now. In fact, we're not going to use px, just a hint. Okay, so great. Let's look at our equation now. So we have our sum of our forces is equal to 0. Is equal to 0. Well, let's pick a direction and start summing our forces in that direction. I'm going to pick the y direction. So we can say that the sum of the forces in the y direction is equal to 0, equal to, and now if we do that, we know that this pressure in the y direction, Py, that's acting in the positive direction, so we can just leave it as Py, times an area, which is going to be delta z times delta x. delta z times delta x. And then there's going to be a negative force in the y direction, which is going to be ps times delta s delta x, which is this area here. Let me draw it in green. This area here. But we only want the y component of that, right? So if we only want the y component of that, we have to multiply it by the sine of theta. So we multiply it by the sine of theta. Great. But the important part about this that we have to remember is that ds times the sine of theta is really just dz. This is dz. Delta z. So if 0 is equal to this, we can cancel those out. And we find out that delta z, py is equal to ps times ps. And we're done. That's actually it. Now, since we included theta, but we didn't specify it, this basically means that no matter what theta is, if it's 90, if it's 0, anywhere in between, no matter what we make the angle of this, ps is equal to py, which shows that that there is no, therefore, no dependence on theta, which is important because since pressure has no direction, it is a, all right, here's where you fill it out before I do. There's a special word we're looking for. I'll even circle it before I write it in purple. Give you an idea of how long it is. What is a quantity, a physical quantity that has no direction? And as opposed to something that has direction. All right. The answer we are looking for is a scalar. Pressure is a scalar quantity. Cool. So if we want to prove that delta P is equal to rho GH, we're going to have to use a different tool. And the tool we're going to use is something called a differential fluid element. Now, a differential fluid element is basically a segment of fluid that is so small that each of the sides is a differential length, so a dx, dy, or dz, right? And we use the same definition you learned in calculus for a differential length, right? It's infinitesimally small. So that would mean that this, let's just try to be consistent with our colors. That means this length here is a d dz. This is a dx, and this distance here is a dy. And what's important about this is, like, let's say we have a quantity, a physical quantity that is varying with position, like this red line here. So this red line, let's say it's, let's actually call this, let's say it's pressure. Let's say pressure is varying in the y direction like a parabola, right? And let's pick a small section of that parabola and let's put this differential fluid element here, and what's it going to look like on this small section? It's actually, I mean, it's infinitesimally small. So it's, if anything, it's a speck. It's a little tiny speck. So what does this curve look like inside of this differential fluid element? Try to draw it. Try to think of if you take even the most curved section of this, which is near the bottom. If we take that and take the smallest little section of it, what does it look like inside of this fluid element? Well, it's going to enter on one side. going to leave on the other higher, right? And inside of it, it's going to look, well, pretty much like a straight line. It's just going to enter and leave, and you're not going to be able to see any curvature because the distance that you're looking at is so small. So if you were to do this fill in the blank, what are those things called where you can just pick words and then plug them in? I can't remember. I haven't had enough sleep. But try to fill in these blanks here. A differential fluid element is so blank that anything varies blank across the element. Okay? So we've already talked about this one. It's infinitesimally small. That anything varies, and then we said that this varies like a line. So what's the adjective for varies like a line? It varies linearly across the element. Great. So now we have this, now that we've explained what a differential fluid element is, and we'll use this several times in the class. So hopefully you didn't just skip over that section. Because it's important to understand what a fluid element is and why it's special. So now let's derive the relationship between depth and pressure using a differential fluid element. What model can we use to relate pressures and gravity? Well, we really only have one model right now, and it's the Swiss Army model of mechanical engineering. We're going to say that our answer to this is sum of our forces is equal to mass times acceleration. Great. We're going to call this equation 1. And what do we need to assume in order to use this? Well, right now, currently in this class, we're dealing with fluid statics, and we know that our fluid is static. We're trying to derive a relationship between depth and pressure for fluids at rest. So our first assumption is going to be that the fluid is at rest. And we're going to label our assumptions with letters. So our equations, we're going to label them with numbers, and our assumptions, we'll label them with letters. And let's also assume that our density is equal to a constant. Call that B. And that gravity is equal to a constant. We'll call that C. Great. So let's now go to, we have sum of our forces equal to mass times acceleration. At this point in your career, it should be a knee-jerk reaction to start drawing a free body diagram. Free body diagrams are quite possibly the greatest tool you'll learn in your engineering education. I don't know what that says about your education, but it is the greatest tool you will learn. So let's draw our forces on this differential element. Again, we're not going to draw all of them because there will be 6 arrows and a lot of things written down on here. But let's draw first our, I like to draw our forces in red. So we're going to draw the one body force going down because we have mass times, gravity acting on our system. And that is going to be rho times g, but we need a mass times a volume. Sorry, it's a mass times gravity, right? And well, we have a density times gravity, so that means we need to multiply it by a volume. So what's our volume going to be? Well, we know it's a differential fluid element, so it's going to be a delta x, delta y, delta z, right? Again, our dimensions on our fluid element are, well, I'm not going to draw them in because things get really complicated, but it's delta z in the z direction, delta x in the x direction, delta y in the y direction. So now let's draw pressure in the x direction, right? We have pressure acting on these faces of this fluid element. And what we're going to do is we're going to write our pressures relative to the middle of this fluid element. Okay? So we have a pressure P in the middle. So the pressure acting on this face here on the on the y, we're going to do apparently we're doing the y. I kept saying x. We're going to do the y pressure acting in this direction. So we know that the pressure here, this force is equal to the pressure, P, but it's going to change as it goes across this fluid element, right? So we have the pressure in the middle, plus some change in pressure with y, dp dy. Okay? But that's just the slope. That's just how the pressure is changing across our fluid element. In order to get the actual amount of change, we have to multiply the slope by a distance, right? So we're going to multiply our dp dy, which is our slope, times a delta y, divided by 2, because we're only going half the way across this cube, right? We're going from the middle here to this edge over here, and this distance from here to here is delta y divided by 2. Great. So that's our pressure. Now to get it to be a force, we have to multiply by an area. And the area that we're looking at is going to be this area here. So that is going to be a dx times a dz. Delta x, sorry, times a delta z. Great. And we can do the same thing now with the x direction, only let's, again, I don't want to draw all 6, so let's actually draw the x direction from the backside here. So we're going to draw it acting in the positive direction. This x was the y force here was acting in the negative y direction, but this one's going to be acting in the positive x direction. And so this one is going to be, our force is going to be equal to our pressure, which is P. Remember, we're starting in the middle. It's the same for everything. In every direction, the pressure is the same. That's rule number 1 of hydrostatics. And there's only one rule. It's rule number 1. Now we've got to add a change because we're on one side of it. And unfortunately, we're in the negative direction now. We're on the back side of this cube, right? We're going from here to the back. So we're going to have a minus dp dx times delta x over 2, right? Because if the pressure is rising in the x direction, on this side, acting in this direction, we would be adding that change, and on the back side, we have to subtract half that change. So we have a dp dx, which is the change. Let me write that a little bit more clearly. We have a dp dx, which is our change in pressure in the x direction across our differential element, times the distance across half that element, because we're starting in the middle and going to the backside, and it's negative because we're going backwards in the negative direction along the fluid element. Okay, we have to multiply that by an area, which is just going to be a delta y and a delta z. And I'm going to leave the z direction as an exercise to you for a second. I'll draw the arrow, and I'm going to have you do both of them though. We're going to go from the top and from the bottom. So from the bottom, I'll do that one, and then I'll have you do the top one. So from the bottom, we're going to have our forces equal to a pressure in the middle, of course. They all start with the same way. Plus, we're going to, on the bottom side, so we're going down, so we have to subtract it. We have minus delta p dz times a delta z divided by 2. And we have to multiply by the area, which is just a dx dy. Now you do this one. You do the negative facing pressure on the top face of this cube. I think I better just pause the video, and I'll start writing it now. All right, pause the video, do it, and then start the video. Okay, so this is going to be equal to a pressure, as always, plus dp dz times delta z over 2 times delta x delta y. Great, so we can extrapolate this to the x and y direction for the other forces, and we have a total of 6 forces acting on this object. Great, so let's pick the one direction that honestly matters in this case, because we were trying to figure out the relationship between pressure and depth, so we're not going to really care about deep pressure in the x direction. So if we take our equation 1, let's call this equation 1, and we're going to say sum of our forces in the x direction is equal to, we've got to write all of our forces in the x direction now. So So we have negative rho g times delta x, delta y, delta z. And notice that we have to assume two things here, that rho and g are constant. That's why we just left them as constants here. And we're denoting that with b and c. There's two reasons we're doing this, right? We're being very explicit about our assumptions. The first altruistic reason is that some point in the future you're going to be working on a large project with lots of other people, and you're going to be taking notes, and somebody's going to look at your notes and they're going to know exactly why you did what you did, right? And so it's always good to be explicit about the assumptions that you are making. Eventually in this course, we'll talk about how the assumptions you're making, for example, here, look like when you're doing like a computational fluid dynamics package using those, right? You still make assumptions. They look a lot different, right? They ask you what options you want to use. They're still assumptions, so you have to be very explicit about the assumptions you use. So that's why we're doing it here. The second reason is much more pragmatic, and that is that our graders are going to be looking for this, right? They're going to be looking for if you're using your assumptions correctly and labeling them correctly, and you want to be as explicit as possible so that you get as much partial credit or full credit as you can. Yeah, so great. So now we got to add our pressure forces. Our pressure forces here, we have one on the bottom acting in the positive direction, so we're going to have plus P minus dP dz times delta z over 2 times dx, delta x, delta y. And then we have one acting on the top face going down, so we subtract that, minus P plus delta, sorry, not delta z, d, oh my gosh, dz, oh my gosh, okay. So I just started thinking like this is probably a lot less annoying when I'm doing it in person, but in a video it's got to be infuriating. P plus dP dz times delta z over 2 times delta x delta y. Great. So, and this is going to be equal to mass times acceleration, but we have assumption A, which makes this 0. Cool. So now let's tell our grader and our future coworker that we're going to take equation 1 and we're going to turn it into equation 2. And that equation 2 is going to be sum of our forces in the x direction is equal to 0 is equal to, well, we can cancel out our pressures because we have a plus pressure and a minus pressure here. But the minuses mean so our oh wow, mean that our dP dz's don't cancel out. So we're going to end up having a negative rho g delta x delta y delta z minus a dP dz times delta z, and the over 2's cancel out because we have two of them, so we're going to get the delta z times delta x delta y. Great. This is the best. This is the best thing in the world. Canceling stuff out. Boom, 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 boom. Now we have some of our forces in the. Again, we have to tell them that we're taking equation 2 and converting it into equation 3. Our delta. Some of our forces in the x direction is going to be equal to 0 is equal to negative rho g minus dP dz. Great. So if we rearrange this, we get that our dP is equal to a negative rho g dz. Now, hopefully at this point in your career, I'm going to stall here for a little bit, and you're going to like look at the screen for a bit, and you're going to look down, and suddenly your hands has already started integrating this because we've got a nice separable integral here, which means we're going to integrate it. So we're going to integrate from P1 to P2, and and we're going to integrate this side from H1 to H2. And the result that we're going to get is that P2 minus P1 is equal to negative rho G H2 minus H1. Or, if you don't like having that negative sign there, we could also write it as P1 minus P2 is equal to rho G H2 minus H1. This is the one you traditionally see, but it's a little tricky because you have to remember that the 1 comes first on this side, but it comes second on that side. So let's talk a little bit about how these two models can help us predict behavior. Oh, a quick note. When we did this integral, one of our assumptions was that our density was constant and our gravity was constant, right? Which means that if we have, let's say, a container with oil on top. Let's put oil up here. Got some oil. We got some water on the bottom, like this. If we wanted to figure out the change in pressure from H1 to H2, we can't go straight from H1 to H2 because the density, as we go in this direction, changes, right? We have a rho water and a rho oil. So what we have to do is we have to go from H1 to an H2, make this an H3, and we have to do it twice. So we can do a H2 minus H1 from here with a rho water, and then we can go from H2 to H3 to get another delta P, and eventually solve for it. But you can't go the whole way. Anytime there's a change in density, you have to start over. And if your density varies continuously, because, for example, you're looking at the atmosphere, well, then you can't use this at all, and you have to go back to this equation with the integral and integrate it, but with a variable density. And it gets much more complicated. And at that point, your gravity might be changing a little bit too, so you want a formula for gravity. It gets crazy. All right, so let's talk about how these two models can help us predict behavior. Question, what is the water height in the other three tubes? If we know we have a static fluid and our water height is here in this tube, what is going to be the water height in all these three tubes? Go ahead and draw it. Now, intuitively, we know that if we fill up this tube and we have a U tube, the water height, doesn't matter what the diameter of the other one is, the water height stays the same. Doesn't matter what the diameter is, the water height stays the same. In here, it doesn't matter what the path is that it takes to get to it, the water height stays the same. And the reason for this is that in a static fluid, remember the pressure is the same no matter what direction we go. So at this point, below all of these tubes, we have the same pressure down here. And which means that we have to have the same height of water above every single one of these points down here on the bottom. So it's trivial. Here, it doesn't matter what path the water takes. It just matters how much water we have above it. Okay? What the height of the water is above it, not the total volume of water above it. And I don't know if this actually happened. I can't find anybody who actually can I can't find anyone who's found a real account of this happening, but everybody calls it Pascal's barrel buster. And supposedly Pascal came up with this relationship that the change in pressure is only equal to rho g times h, and everybody was like, you're so full of it. That can't be true. If we have a barrel, I'm not going to draw another barrel I'm going to draw it, but I'm going to draw it quick. If we have another barrel like this, and we put a very big tube above it, like this, huge tube full of water, like this, clearly the barrel is going to break with the bigger tube at a lower height than the smaller tube, right? So if we compare these two, we'll say, oh, it only needs about this much water to break a barrel with this diameter, but we need this small little capillary tube here to be 30 feet tall, right? And so apparently Pascal set up this very dramatic experiment where he did it in front of the king and all his court. I'm not really sure. But he did a very dramatic experiment where he set up the barrel in a street, went up to the top of a building and filled a thin glass tube with water that was sealed at the top of the barrel. And as the water filled up the tube, eventually the barrel just broke and exploded. And everybody was like, "Oh, you're right, Pascal." Again, I don't think that happened. But we know that the pressure in the barrel, right? Let's say the pressure right here inside the barrel is equal to the height of the fluid, and that's it. So it doesn't matter how thick this is. We know that the pressure in here, the delta P, is equal to negative rho G delta H, right? And the reason it's surprising is intuitively you think it'd be equal to the weight of the fluid above it. And the weight is equal to the density times the volume times gravity, right? But it's not equal to the density and the volume times gravity. It's equal to the density and gravity times just the height. So that's why it's so surprising. And there's actually, let me see if I can, I'm not sure if I can put links into my YouTube comments. I'm going to try to. There's a woman, professor at, I can't remember the university, but she did this. She set up, took a long, thin plastic tube and a glass, a giant glass beaker. And she tried to fill up the tube with fluid and show that it would eventually break it. And it was actually a fascinating study in fluid mechanics because it's very difficult to fill a very long, thin tube full of water. So she would fill it, the water, and you're going to see this happen. The tube is long and thin. The water would form a plug like this, and it would flow down the tube, and it would compress the air, and then it would compress it just like a spring. And what's going to happen if you put a weight on a spring and drop it? Well, it's going to come back up, right? And so she'd fill it with all this fluid. The fluid would go down, and then it would start coming right back up the tube and spraying everywhere with water. So it was actually quite difficult to fill the tube with water, but she did, and eventually she got it all the way full, and eventually, well, I've given away the climax of the YouTube video because we've just studied this, but eventually the glass bottle breaks. So like I said, I'll try to put a link to that in our in the comments of this. So the next part of this is what I call quiz not quizzes. When I do this in class, I have you guys work in groups, and when we have during our in-class synchronous lecture about this, I'm going to have you guys do breakout groups and do this in class, right? So I'm going to make the solution to this a separate video so that you can watch it later if you want to. But what I recommend you do is not watch the next video before class, and instead try it on your own at home using the scaffolded notes, and then go to class, work on it with other people. Again, we're trying to do that engaged learning because we don't want to spend any more time on this class than we have to. You have enough going on, especially in freaking 2020. Well, now you know when I record this video. Let's see how often I re-record it. So again, we want to do this engaged learning. So in class, I'm going to make breakout groups, and we're going to try to do it together, okay? But I'm going to explain it real quick to you. Well, no, I'm not going to explain it. We're just going to go on to the next video. Okay.